Well, good afternoon. It's 12:37. I'm 7 minutes late getting started. I don't know where all the students are. I'd been in once and no one was here, so I thought, well, let me run down the hall and take care of a couple things, and then came back and still nobody was here, so we're going to get started without you. I'll hang off on any announcements until somebody gets in the room to hear them, but other than that, we'll get started on math. Calculus 3. So here we go. Chapter 11 has been Vectors in the Geometry of Space, and we're starting 11.4 today, the cross product of two vectors in space. Now remember earlier, way earlier, we had talked about a scalar product. You have a vector multiplied by a scalar, you multiply every component in the vector by that number, whatever that scalar number is. That's called a scalar product. Then we came across the dot product, which is a way of multiplying two vectors together. So when you multiply a scalar times a vector, you stay with the vector. You just scale it up or scale it down. Then when you do a dot product, which is multiplying two vectors together, you get a scalar, okay? You dot two vectors and you wind up with a scalar product, or a scalar as an answer to the dot product. Now we're going to do cross products. And the difference here is you're multiplying two vectors. Now it's a different way of multiplying than dot products are. You're multiplying two vectors and you're coming up with a vector, okay? And this is a cross product. And many applications in physics, engineering, geometry involve finding a vector in a space that is orthogonal to two other vectors that you know, two given vectors. And this will be the cross product. That's what we're studying here. Because the cross product yields a vector, sometimes it's called a vector product, okay? The problem with calling it that, then if you start to call a dot product a scalar product, because you get a scalar as an answer, then you confuse that with a scalar product, which is multiplying a scalar by a vector. So just be careful on those choices of names. So our objectives here is to find the cross product of any two vectors in space and use the triple scalar product of three vectors in space. A triple scalar product of three vectors in space. So let's start with the cross product. Okay, I'm sorry, I've already read this. Many applications in physics, engineering, geometry involve finding a vector in space that is orthogonal to two given vectors. In this section, you'll study a product that yields such a vector. Now, I've already done that whole page, so I won't do that again. All right, so here's your definition of a cross product of two vectors in space. So here's one vector, u1i plus u2j plus u2k, 3k, I'm sorry. Now, by the way, this could work for a two-dimensional vector as well as a 3, okay? But we'll stick with 3 right now. And then vector v is v1i plus v2j plus v3k. Pretty similar to what we've been calling vectors before. Both of these are vectors in space. The cross product of u and v is then a vector, and this is how you do it, but this isn't the easy way to do it. U cross v would then be u2v3 minus u3v2 times in the direction of I minus u1v3 minus uv31 in the direction of j, and u1v2 minus u2v1 in the direction of k. It is important to note that this definition applies only to three-dimensional vectors. This won't work for any higher dimensions nor lower dimension either, I don't think, okay? Only three-dimensional vectors, okay? All right. There's got to be easier way than memorizing u's, 1's, 2's, 3's, and v's, 1's, 2's, 3. And there is. Here is the convenient way to calculate a cross product in 3 space, okay? And again, this only works for 3 space. All right. Now, I'm trying to think in this course if we've hit determinant before. I know in other courses we have. I'm trying to remember if we have in this one. I don't think we have. But here's what a determinant is. It's like a matrix, only we don't close in our ends. We just put the straight bars there. It kind of looks like the absolute value of an array of numbers, okay? And that's not what it is. It is actually a determinant. And here's what the determinant is. To get the I value here, wipe out the first row and the first column. And the I value would then be the cross product of U2 minus U2 V3 minus U3 V2, okay? And that's where you got this term, okay? It's the downward diagonal is positive, the upward diagonal is negative. The anti-diagonal, or whatever you want to call it, is negative, the product of those two. Now, here's one way to do this, and you have to remember, alternate your signs between these components. That's one way to think of it. For the J component, wipe out the first row and the second column, and then do your same cross product here. The downward U1 V3 minus V1 U3. Okay? And then that's times J. Then you go back and multiply it by that. And then alternate the signs, so it was plus, minus, now plus again. We're doing the K, so wipe out the first column and the third row. And then you have U1 V2 minus U2 V1. And that's what you get down here. Okay, and that gives you this. Now, that's one way to do it. Well, they're doing it that way, but doing an extra step in there. And, whoops, I didn't pick my eraser. Okay. Here's what their extra step is, and it's absolutely correct. What you have left here is I times this determinant here. And they put the determinant first, because the determinant is just a number. And then this is, like I said, down diagonal positive, up diagonal negative. Then alternate signs, and then you have this one here, and go like this. You see, this is exactly that. These are exactly that. Okay? And then, again, down diagonal is positive, up diagonal is negative. Okay? Now, that is a way to do it. I feel like there's an even easier way. This way eliminates the need for having to remember to alternate signs. And let's see. Now, sorry. Note the minus sign in front of the J component. Each of the three 2x2 determinants can be evaluated using the diagonal pattern. The down diagonal is positive, the up diagonal is negative. Okay? So, some examples. 2 times negative 1 is negative 1, minus 12 is minus 14. Okay? 4 times 3 is 12, minus 0 is just 12. Okay? Those are just a couple of examples. Now, I'm going to show you another way to do the same thing, and it starts off looking like we're going to do the same thing, but it's just a slight little twist. Okay? And let's use these two vectors to do what we're talking about. U cross V. Well, what we said before was let's write the determinant of I, J, K. Now, my modification to this, and it's ever so slight, and it seems a bit bizarre, but it works. And that is repeat the I and J. Okay? You don't need to repeat K. Okay? Now, the one that's first, and by the way, the order in cross products matters. It doesn't in dot products, it does big time in cross product. I'm sorry, that sneezing I did now, my nose is running like a fountain, so I'm sorry if I'm breaking in between here. All right, now you put your components under the I, J, and K. And you put U first and V second because it's U cross V. Always the order matters. Okay, so you have 1 minus 2, 1. Repeat the I and j, 1 minus 2. Then you put the v vector, the second vector, on the bottom row, and that's 3, 1, negative 2. And then repeat I and j, 3, 1. Okay? Now, this looks strange, doesn't it? But here's what works. The I value here just go down like this. Okay? And that gives you 4i. Okay? Then for j, you go down like this, and that's plus 3j. Don't have to worry about changing signs or anything. Okay? And then k, do down like this, plus k. Okay? Now we go our up diagonals, and these are always negative. So I'm going to take off my construction lines here that was helping you see what to multiply. Okay? And, okay? Now we'll do the up diagonals. Well, this up diagonal is going to k, so that's but it's negative. Now remember, up diagonal is negative, just like before. So this would have been a minus 6, but it's up, so that's a negation of that. So that's a plus 6k. And here's your up diagonal going to I, and that's a minus I. And then you have an up diagonal going to j, and that's a minus 2, but because it's going up, it becomes a plus 2j. All right, then you add your components. That would be 3i plus 5j plus 7k. Okay, now let's see if we got the same thing they did. I hope we did. It's been a long time since I've done this. 3i plus 5j plus 7k. Perfect, right there. You didn't have to remember about changing signs or anything else. The middle term, you just do your 3 down diagonals are positive, the 3 up diagonals. I'm sorry about the interruptions here. I may have to stop a moment and go to the restroom and clear my head, but let's see if we can keep going. All right. So there's your A part. Now, if you like the other part better, go for it. You know, it works just the same. This, to me, though, you don't have to cross out rows and columns. You don't have to do any of that. You just do down diagonals, positive, up diagonals, negative. All right. Now, like I said, the order matters because the next one, now I'm going to erase what we got here. Well, actually, let's make it a little smarter. Okay? We'll keep the form here, but we're going to reverse the 2 vectors. Now we're going to do the B part, which is V cross U. So this will be, we'll swap and make this 3 and 1. Okay. We'll swap these 2 and make it 1 and negative 2. We'll swap this and make it negative 2 and 1. And we'll swap those 2 again. We'll just repeat those 2 so I don't have to worry about keeping up. 3, 1, you just repeat these 2, 1, negative 2. Okay? Now, what I'm going to do now, and it's not really very fair, but I'm going to do it because I know what the answer is. Okay? All right. Again, do your downs, and you get a 1i. Down is a negative 2j. There it is. And a down is a negative 6k. There it is. Then do your ups. That's a minus k. That's what we got here. Ups. That's a minus a positive 2. So that's 4. Minus 4i. There it is. And then you have a minus 3j, because you're going uphill, minus 3j. There it is. And now what do you have? Minus 3 minus 3i minus 5j minus 7k, which is exactly the opposite of u cross v. Now, does that just happen to be because of these two vectors? No, that is a rule. U cross v is always the opposite of v cross u. Only time it is if one of these vectors is a 0 vector, and we don't usually go around messing with those. Okay? So, it does matter what order you do, because if you do the wrong order, you're going to get the negative answer. Okay? Now let's do v cross v. Okay? So again, we start off with your I, j, k, and repeat the first two columns, I and j. Okay? And then it's v cross v, so that's going to be 3, 1, negative 2, repeat the first two, 3, 1. V cross itself, that's going to be 3, 1, negative 2, 3, 1 again. Okay? Now let's go to town. Okay? Down diagonals are positive, but that happens to be a negative, so the positive and negative is negative. So that would be a minus 2i minus 6j plus 3k. All right, now let's do the up diagonals, and this will be 3 times 1 is 3, but it's going up, so it's a minus 3j, k. And then the next up diagonal is this one, and the product is negative 2, but since you're going up, it's the opposite of that, so plus 2i. And then the last one is a minus 6j, but because it's going up, that becomes a plus 6j. Uh-oh, when you add these together, what do you get? You're a good old 0 vector, because 0i plus 0j plus 0k. No components at all. Okay? Now, there's a reason for that. I don't know if you recall, but in the dot product of two vectors, you got... Sorry. Goodness gracious. Okay, you may not have remembered this, and I may have to stop in a minute, but wow. You get the maximum dot product if the two vectors are collinear, or in the same direction. You get a 0 dot product if the two vectors are perpendicular to each other. Well, guess what? In cross products, you get the maximum vector magnitude, because you see, dot product of two vectors gives you a scalar quantity, so you get the maximum scalar number when they're in the same direction or parallel to each other, and you get 0 with they're perpendicular. Okay, but those are just numbers. Okay, if you're doing a cross product, you get the maximum vector length if the vectors are perpendicular to each other, and you get 0 if they're parallel to each other. Okay, so the cross product of two parallel vectors, and of course the vector cross with itself is parallel, I mean, by all means, and that gives you a 0 vector, not the number 0, 0 vector. Okay, now we're going to watch how they did it, and you tell me whether you like my method or theirs better. It's not my method. It's one they use in physics a lot. I don't know who came up with it. But here's U cross V. You set up your determinant this way, and then you do, when you cross out the first row, first column, the leftover determinant is -2, 1, 1, -2, and that's multiplied by I. And if you wipe out the first row and second column, the determinant that's left is 1, 1, 3, negative 2, but you're going to have to negate that one. And then the third one, when you wipe out the third column in the first row, you get 1, negative 2, 3, 1. That little determinant, and then the determinant of a 2 by 2 is just the product of the down diagonal minus the product of the up diagonal. So that would be minus, goodness gracious, oh man, that'd be 4, I can't talk. The down diagonal is 4 minus 1, so that would be 3i. And then you have a minus here, that's a minus 2, minus 3 is minus a minus 5, so that's positive 5j. And then this one would be 1 minus negative 3, but minus a minus is plus, so that would be plus 7k. All right, and that's the same answer we got before. Depends on which way you like better. You have to do determinants this way. You have to do something like a determinant the other way. Just completely up to you, whichever you prefer. All right. When you do, oops, let me get mine out of the way. Sorry. I can't talk worth a toot now. So 4 minus 1i minus a negative 2 minus 3j plus a 1 minus 6 k. So that, 1 plus 6k. Sorry, I'm going to have to go blow my nose, I think. So that gives you 3i minus a minus 5, which is plus 5j, plus 7k, which is exactly what we got the last time and previous time here. Okay. Let me pause this. I'll be right back as soon as I can. Sorry. All right, I'm back. I'm not totally better, but at least I cleared out some, so sorry about the inconvenience there. Okay, let's do the V cross U, and we'll do it their way. They'll do it their way. And let's just review this quickly. To get the I component, wipe out the first column, first row, and that would then be the determinant of 1 minus 2 minus 2, 1 times I. I can't write I. Okay, and then we do the same thing with J and K, so I won't do that. This is how they proceed. But remember, they always have to negate the J, okay, the middle one. So I'm going to erase what I just did, and you'll see they do the same thing, writing the I a little better, though, and that's what they get there. The I is there, the J negative in front, and then the K. And you get each of them by wiping out the row and column for that unit vector, okay? And then you get the determinant. Then once you got the determinant, you do the calculations. 1 minus a positive 4 is minus 4. I minus 3 minus 2 minus a minus 2 J plus minus 6 minus 1 K, and sure enough that gives you minus 3i minus 5j minus 7k, which is exactly the negative of U cross V. And it's not just happenstance, it happens every time. Okay? V cross V, on the other hand, like we saw, again, if you do the same deal, then you're going to, well, they don't even show you. You come up with the zero vector. Notice that's bold, so it is a vector, not a scalar. Okay? So here are the algebraic properties of the cross product. U, V, and W all be vectors in space. We'll assume three-dimensional here. C is going to be a scalar. Okay? Now, Now, I said before you could do a cross product with two-dimensional vectors. You really can't, because your third vector has to be perpendicular to the other two, and you don't have but two dimensions to begin with. So you have to be in three space. Okay, sorry about that. Okay, C is the scalar. So U cross V, as we just saw, is exactly the opposite of V cross U. Okay, now, this is sort of a distributive property. The second one is. U cross the sum of two vectors is the same as U cross the first plus U cross the second. Just about like you would expect a distributive property to be. Remembering that when you add two vectors together, you get a vector, and then when you cross two vectors, you get a vector. So when you cross two vectors, you get a vector. Cross another two vectors, you get a vector. Add those two together, you get a vector. So everything's a vector in that. Okay, number 3 is the sort of the scalar product rule for a cross product. Okay, and let's see how that goes. The C, some scalar, times the cross product of U cross V, which remember is a vector, is the same as C U cross V, and that's exactly the same as U cross CV. I had to stop and pause and make sure. Notice here, it's U cross V here, so it has to be U cross V here, and it has to be U cross V there. You can't reverse them, because if you do, you're going to wind up with a negative. So you have to keep the order exactly right. Okay? And then, of course, U cross the zero vector, of course, is the same as 0 cross the U, zero vector cross U, and that's 0, because you can't get anything else. All your components of the zero vector are 0, so crossing them is going to turn everything 0. But U cross U, or V cross V, or W cross W, anytime there are two vectors in the same direction cross each other, that's going to give you the 0 vector as well. All right, now we have one more, and this is the how you deal with a dot and a cross product. Now, the order of these certainly matters. That would be U dotted with the cross product of V cross W. Number 1, V cross W is going to be a vector. Of course, it's a cross product. So, V cross W is a vector, and U dotted with V cross W is going to give you a V cross W is a vector. You dot two vectors, U dotted with that vector. That's going to be the same as if you do U cross V and then dot it with W. Now, it's not maybe entirely obvious why that's true, but it is. But notice you couldn't do it the other way. You can't move the parentheses here and get that to work. It won't do it, because this is U dot V. U dot V is a scalar. You can't cross a scalar with a vector. Same thing here. You can't change the order here, or you get the same thing. So you have to keep the multiplicative element the right one, okay? And that does give you. Now, I'm trying to remember if I've ever used that sixth principle ever before. I can't recall. I bet you they'll give us an example with it, but I am having trouble thinking of an application in real life where I've used that, and I just can't think of any. All right. Now, the very next page in your book, top of the next, that was bottom of one page, and they did give a little proof for one of those. Now they're doing a theorem here, theorem 11.8, geometric properties of the cross product. Now, again, we got U and V being non-zero vectors in space, meaning three-dimensional, and theta is the angle between U and V. And that's all they tell us, the angle between U and V. And I believe I'm right in saying this, so it may not matter as much as I'm supposing, that it's the smaller of the two angles between the two vectors. It may not matter at all, but I know it works for the smaller of the two vectors, because these two vectors are at a very shallow angle. That's the angle you usually deal with. But the reason it doesn't matter is the other angle is supplementary to that one, and in both the first and second quadrants the sign is positive, so it really is not going to matter, I don't think. So here is your geometric properties. If you have two vectors, any old two vectors in space, the cross product of those two vectors, if it has one, okay, of course if they're parallel vectors, it wouldn't have a cross product. Goodness gracious, I thought someone was coming in the room and it's the wind blowing on the windows. It's a tight old building, of course. Yeah, never mind. Okay, so U cross V is a vector, and that vector is orthogonal to both U and V, perpendicular to both U and V. U and V don't have to be perpendicular to each other, no, but any two vectors out there in space, as long as it's not parallel, any two non-parallel vectors out that you cross them, your cross product is going to be perpendicular to both U and V. All right? The magnitude of that U cross V is going to be the magnitude of U times the magnitude of V times the sine of the angle in between. Okay? Now, remember for your dot product, your U dot V, you didn't need the magnitude on that side because you're already going to be a scalar, was the magnitude of U times the magnitude of V times the the dot product. You don't need the absolute values because it's going to be a scalar. So the dot product of U dot V is going to be magnitude of U times magnitude of V times the cosine of the angle in between, not the sine. Okay. So that is another difference in dots and cross products. Okay. Let's see. Now, U cross V is equal to 0. Remember, U and V at the very top says they're non-zero vectors. So then if U cross V is 0, that's only true if they're scalar multiples of each other. In other words, they're collinear. Another way of saying it, they're in the same direction, though they may, well, along the same line, even though they may be in opposite directions. So lots of ways of saying that. Scalar multiple, the scalar could be positive or negative, meaning in the same direction or the opposite direction, but they would all be collinear. And then the magnitude of U cross V is the area of the parallelogram having U and V as adjacent sides. Okay? So, I think we'll see more of that later. Okay, so here we go. Now this is the bottom part of page 781. Both U cross V and V cross U are perpendicular to the plane determined by U and V. Remember we said cross product is going to be perpendicular to both of the other vectors. Okay? But we know they are not the same. So basically what you have, if you remember, if two vectors anywhere in space, if you only have two vectors there, they are going to define a plane. Okay? Just like 2 points on a plane will define a line, you know, as long as they're not the same 2 points. Well, two vectors in a plane, see, how was I saying that? As long as they're not parallel to each other, two vectors are going to define a plane. Okay? Now, the cross product will then be perpendicular to that plane. Has to be, because it's perpendicular to U and perpendicular to V. But why do we get two results? Well, one's coming on one side of the plane and the other's going on the other side. One way to remember the orientations of U, V, and U cross V is compare them to the unit vectors I, J, and K, and realize this, and here I'm going to write it. I'm going to do it slightly differently from what they do. I like to write it this way. I cross J is equal to K. Now that's exactly what they have here, except they put the K in front. You might say it doesn't matter, and it doesn't. But notice the order here, I, J, K. The next cross that works is J cross K is equal to I. So, again, keep the order right. I, J, K, I, J, K, I, J, K. Okay? I'm feeling lousy. The third one of these, I hope you're picking up the drift of it now, is that K cross J, cross I is equal to J. Again, you keep the order I, J, K, I, J, K, I, J, K, and that's what you've got here. If you reverse the order, okay, then you wind up to the minus. So J cross I is minus K, okay? And K cross J is minus I, and I cross K is minus J, okay? Now, part of that gets back to, in fact, just about all that gets back to what we call the right-hand rule, okay? Now remember how he did it in the book originally? He said, stand on a corner and let your right arm be going up the first wall, your left arm the perpendicular wall to that, your head is facing up the positive direction from there. Well, if you just use the goodness gracious, I'm having trouble breathing. If you that was the way they described it, you know, right arm and left arm, and then your head's pointing upward in the positive K direction. How I like to do it, and this is how I learned it, is point your fingers in the direction of the eyes, cross, in other words, bend your fingers in the direction of J, your thumb on your right hand will be pointing upward, and that's a right-handed system, okay? If you did a left-handed system, which I just assume they didn't do, you would then point your fingers in the direction of I, and then bend them in the direction of J, and that, by the way, would turn out being a much if you did the left hand root, point your fingers to the left hand direction of I, bend them, that now is in the direction of minus, you have to turn your hand over. Point your fingers in the direction of I, bend them to a positive J, you have to turn your hand over, and now your thumb on your left hand is pointing downward, and that's a left-handed system. So they say the three vectors U, V, and U cross V form a right-handed system. U and V don't have to be perpendicular. Most of the time they're not. But U cross V will be perpendicular to both of them. So when you point your fingers of your right hand in the direction of U and then bend them in the positive direction of V, then your right thumb is going to point in the direction of the right-handed rule system. And that will be pointing in the correct direction. So, here's example 2. Find a unit vector that is orthogonal to both U and V. Well, first you got to get a vector that's orthogonal to both, and how do you do that? Let's call this vector W. Vector W, to be orthogonal to both of those, must be the cross product of U cross V. Okay, and they just say a unit vector, it's not the unit vector. it could be the one pointing one way or one pointing in the opposite direction. It really doesn't matter, but let's just choose it this way. So what would that be? Let's put our determinant looking straight line black bracket there, sorry. Put our I, J, K, and repeat the I and J. This is how I like to do it. If you like to do it the other way, go for it. It's fine. And then we want U, whose components are 1, minus 4, 1. And then repeat the 1 and minus 4. Okay? Then the V vector are 2, 3, and 0. Notice this one doesn't have a K component. That's fine. That means the vectors all contained in the XY plane. There is no component in the Z direction, which is perfectly okay. But you have to put a 0 there for the K component. Okay? Then repeat the I and J, 2 and 3. Okay? Now all we're doing is finding a vector orthogonal to these two. Later we'll make it a unit vector. So in the I's, that's going to be a 0I. J, that's going to be a 2J. And K will be plus 4K. I swear, this pen is not writing well. Man. Whew. I may have to pause again just to clear my head one more time, because this is really okay. Let me start that one, the second part, over again. We're doing the J part now. Oh yeah, I'm sorry. 0I plus 2J, and I was right, plus 3K, because that's the downward diagonal. Now go with the upper diagonals, and that's going to be a minus 8K, so that's going to be plus 8K. Upper diagonal here will be a minus a 3I, so that's minus 3I. And then finally the last one is a 0 again. Okay? I started to put a sign there, but I don't need it back. Okay, sorry. Goodness gracious. All right, now what do we have? The vector that's perpendicular to both of those is minus 3I plus 2J plus 11K. Now, what we need to do is make that into a unit vector. We need that direction, but I can't read my writing here. That's 11K. But we need it as a unit vector. How do we get it to be a unit vector? Divide by its magnitude. What is its magnitude? The square root of 9, that's 3 squared, plus 4, which is 2 squared, plus 1, 21, which is 11 squared. Okay? Now, when you add those together, that's 125 plus 9 is I think the easier way to do that would be 121 plus 9 is 130 plus 4, 134. Not a perfect square, so this will be minus 3 over root 34 I plus all right, wait a minute. Oh man, my head. Yeah. plus 2 over root 34 j plus 11 over root 34 k. Okay. Let me get my pen cleaned up a little bit. It just sort of keeps making stray marks. Okay. Now, oh man. If you needed to confirm that as a unit vector, then do the sum of the square of these three components squared. So that would be, and minus times minus is plus, so that would be a 9 over 34, because square root of 34 times square root of 34 is 34, plus 4 over root 34 plus 125 over root 34. Okay. What you would do is do the sum of the squares of each component. It'd be 9 over 34 plus 2 over 34 plus 121 over 34. And again, 121 plus 9 is 130 plus 4 is 134 over 130. I left off the ones, didn't I? I thought something looked bizarre there. These are 134s there, not 34s. Square root of 134. 121 plus 9 is 130 plus 4 is 134. Goodness. This is affecting my head. All right. Well, I was on, oh, there's the example. No? There is a, here's example 2. I have not flipped the page, so I wasn't seeing it. Yeah, so it's minus 3 over root 134i plus 2 over root 134j plus 11 over root 134k. Perfect. All right. That is a unit vector, and it's orthogonal to the other two. Now, if you wanted to check that out, you don't have to, but it's just not too bad of an exercise to do. Do a dot product between u and this one down here. Just see what we get. It's 1 times the negative 3 over 134, so that's negative 3 over 134. Minus 4 times that would be a minus 8 over square root of 134. So that would be okay, let me start over because I think I started crossing up what I was saying. The component here, 1 times negative 3 over root 134 is negative 3 over root 134. Minus 4 times that would be a minus 8 over square root of 134. Okay, so minus 3 minus 8 would be minus 11. And then this one would be plus 1 times plus 11. That would be plus 11 over root 134. That adds to 0. Let's do the other one as well. 2 times minus 3 is minus 6 over 134, plus 6 over root 134, plus 0. Sure enough, the dot products are 0, meaning those are indeed orthogonal. Okay, that was just a very quick check. Let's clear this out of the way and see how they do it. Goodness gracious, my head feels rotten. Okay. Here's the cross product. Now they did this on the last one, but they didn't show it on the slide set. Here is vector u. And this is hard to see too because it's trying to draw 3 dimensions on a 2-dimensional sheet, and it really comes out a bit wacko. But your u vector is plus 1 in x, minus 4 in y, and plus plus 1 in the k direction. And this is their figure here. You see 1 in the x direction would be right here. Move out parallel to the y direction 4 units, 2, 4, and you get there. So there's where you are in the xy plane, that little cross that you see there. Then you go up 1 in the z direction, which is 1 in this direction, so straight up 1, and that's your position 1, negative 4, 1. Now that's the point 1, negative 4, 1. That's why they put parentheses. U is the vector. That would be components in vector angle bracket 1, comma, negative 4, comma, k, close angle bracket. That would be U. Okay. Now the V is in the xy plane. So you go 2i and then 3j, and sure enough, you're right there, 0k, so you're in the plane. Now, the cross product, which we did, which was negative 3, 2, 11, not the unit vector, but the total vector, u cross v, that's negative 3 in x, so that would be back here, then go plus 2 in y, that would be over here where the cross is, and then up 11, and there it is. And sure enough, as well as you can tell looking at this, it does appear to be perpendicular both to j and to, the u vector and the v vector. Okay. Whew, goodness gracious. So that's what their drawing is showing. What they're drawing is pink is the it's kind of the angle up or down, it could be, from the xy plane of the vector in question. Of course, its vector v is in the xy plane, it's neither up nor down. The vector u is slightly up because it has a plus 1 as the z component, and the cross product is then going to be very far up there because it has a plus 11 as its vehicle. As I guess what you would call it, as projection of that vector, u cross v, down onto the xy plane. The pink there would be the plane that is defined by that vector u cross v as you shoot down, straight down to the xy plane. And I'm not quite sure why they pink it in like this. It may help you see it a little bit better. It seemed like to me just the cross there and the dotted line up, that would almost do it for me, but I don't know. Okay. So anyway, you get minus 3i plus 2j plus 11k, and we've already seen how that winds up in that quadrant. Okay. Now, that's the cross product. That's not a unit vector by any stretch of the imagination. So what we do is, to get the magnitude of that, we take the square root of the square of each of the components, the sum of the square of the components, which would be minus 3 squared plus 2 squared plus 11 squared, which we already, determined to be square root of 134. And then divide that cross product vector, minus 3i plus 2j plus 11k, by the root 134, which is the magnitude of the difference there. And yeah, you got it. Okay, so there is a unit vector in that direction, and we've already shown that it is one. All right, in physics, the cross product can be used to measure, let's make sure that we're not skipping something here. Yeah, they are. They're skipping example 3. So let's go back and do example 3 here. I'm sorry, my head is so messed up today. Here they give you the vertices of a quadrilateral. They list them here. And it says, show that the quadrilateral is a parallelogram and find its area. Okay? All right. The vertices of a quadrilateral are listed. It says, show that the quadrilateral is a parallelogram. Now, what that means is the two opposite sides are parallel to each other. And beyond that, it tells you that the two opposite sides have to be the same length as well. Now, this is where I find the slideshow to be a little deficient. If you go back to that theorem 11.8, in the proof of this, they used the fact that you had a parallelogram here. The vectors u and v form adjacent sides of a parallelogram, and the height of that parallel sorry. This is the figure on page 781. I'm afraid I'm going to start clogging up again. Magnitude of v times the sine of the angle theta. Okay? That's the height of the parallelogram. I keep thinking someone's coming in the door. It's just the wind is blowing. Well, no, someone is coming in the door. Okay, I was right. Daniel is here. So far, the only one here. Turn on the closest light to me. Yeah, that. Okay. And I'll turn on the projector. I was just about to pause and run down and get something to drink because I've been coughing and sneezing like crazy the whole period. I don't know why.
Yeah, you can get something to drink.
That's fine. I'll make it now. It's a lot better having someone in the room. Now, this is, okay, I'm sorry. Property 4 was this, that the magnitude of u cross v was is the area of a parallelogram having u and v as adjacent sides. Okay, so they give you, this is example 3, not given in the text. I mean, it's given in the text, not given on the slide set. But remembering this, that u cross v is the area of a parallelogram having u and v as adjacent sides. So what we have to show here, that these are vertices of a on page 782, sorry, section 11.4. Okay, example 3. Kind of the bottom half of the page. 782. Okay. They say these are the vertices of a quadrilateral. And it says show that is a parallelogram and find this area. Now the way to show it's a parallelogram is to show that the two opposite sides have the same magnitude. Okay? Now, and these are the vertices. So let's go back, and here's where we're going to do this. Here are the 4 vertices. I'm going to put them up here. A is equal to, these are points, so as parentheses are appropriate, 5, 2, 0. B is equal to, I'm putting them in a different order. I'll put C here. I'll try to keep it the same way the book is so we won't get confused. Okay. B is 261. C is 247. And D is 506. All right. Now, like I said before, the way you can show it's a parallelogram, the two opposite sides have to be parallel to each other, and they also have to be equal in length. Okay? So, I think one of those implies the other, but let's just show it. So what we're going to do is look at the vectors formed by these. Now, they drew them out, I didn't. So let's look at all the vectors you could get out of here. Let's first look at vector AB. Okay, vector AB would be, remember it's B minus A is how you do it. So that would be a negative 3I plus 4J. Let's just do it in, I mean the book does this, but it's just so much easier to do angle brackets. So that would be a negative 3, positive 4, 1. Okay? Now, AC would be, C being the terminal, that's a negative 3, 2, 7. Okay, C minus A basically. AD would be 0, negative 2, 6. Nothing's coming, well, you don't expect any of those to be anything special. Let's do, we know BA is just going to be the opposite of that one, so we won't do that one. BC would be 0, negative 2, 6. Hey, we can see right now that AD and BC are parallel, exactly the same length. Okay? Done. All right, let's do BD. BD would be 3, what we're doing is D minus B, negative 6, 5. Well, that doesn't give us anything impressive. We've got one more pair to do, and that's CD. So CD would be 3, negative 4, negative 1. Ha! Look at that. It's exactly the opposite of that one, meaning it's just going in the opposite direction, but those are same length, parallel. Okay? So these two are same length, parallel, going in the same direction. Those are same length and parallel, but going in opposite directions because they have exactly the opposite components of each other. So we have two sides that are every opposing side, AB and CD, are opposite sides and they're parallel to each other, and AD and BC are opposite sides and they're parallel to each other. Okay, because the vectors are identical in length and direction. Okay, absolutely identical. So therefore, okay, so it says the vertices are listed below, show that the quadrilateral is a parallelogram. We just did. Find its area. Now that's where we use this, number 4. U cross V is the area of, the magnitude of U cross V is the area of the parallelogram having U and V as adjacent sides. So going back here, we know that these two are, no, scratch that. Yeah, these two are adjacent sides. They share A. Okay? Now, it doesn't matter which one you do, whether you use that one or that one. You know, see, those two share D, these two share A, these two share, no. Again, these two share A, those two share B, those two share C, and these two share D. There, one. So it doesn't matter which two you do, but do these, just do the cross product of these two vectors. So why don't we do AB cross AD? And we're going to do the magnitude of it, so that's going, it doesn't matter which direction we go, it's going to do it. So let's first do AB cross AD. Now we may wind up with a, signs are weird. It doesn't matter. We're going to undo that when we take the magnitude of it. We'll just find that. All right, now you weren't in here when I showed how to do this, but you're in physics, right? Y'all probably done cross products there, haven't you? Okay, here's how you do it. You set up your I. Now, I'm doing it slightly different from what the book does. Not much different, a little bit. J, K, and then I repeat the I and J. I'm pretty sure Dr. Bryant does this too when he's crossing two vectors. Okay? AB or BA or CD or DC, it doesn't matter which one you do, but let's put it down. -3, 4, 1, and then repeat I and J. -3, 4. Okay? Then do AD, or whichever of the others you do. 0, -2, 6, and then repeat I and J. 0, -2. Okay? Now, here's my favorite way of doing it. Do your down diagonals. These are always positive. Okay? That's 24I. Down diagonal here. 0J, because you're multiplying these together. Down diagonal there, plus 6K. The up diagonal here, that's a 0 for the K. Up diagonal here is a minus 2I, but because it's up, you negate that. So that's a plus 2I. Okay? And then you have a minus 18J, but because it's up, that will be a plus 18J. All right. So here is that vector, the cross product of those two, 26I, you add these two together, plus 18J plus 6K. Now that's the cross product. We're really not interested in the cross product itself. In that vector, we're interested in its magnitude. So the magnitude of this is the square root of 26 squared plus 18 squared plus 6 squared. I'll need a calculator for that one. Do you have one? It's going to be a pretty good sized number. Could have factored out a 2 out of each one, but that wouldn't have helped you a lot. 26 squared plus 18 squared plus 36, and take the square root of that sum. Yeah, well, let's just round that to 32. They rounded 32.19, which is fine. But look, nothing they gave us has anything but a single digit. So how in the world are you going to get 4 digits of precision out of that? I don't know. So let's just round it to 32. That's going to be approximately the area of the parallelogram. You don't need to do anything else. It's just got it. Now, the question is that parallelogram a rectangle? We didn't consider that, did we? Now, what would that be true if that was a rectangle? That would mean that any two of these would be perpendicular. Any two of them. Not these two, because they're, no, I'm sorry. No, not that. This and this, or this and that, or, any of the two that aren't the same, okay? So these two. So let's see if they're perpendicular. How do you do that? Dot product will tell you. So do the dot product, negative 3 times 0, is that 0? Hey! 4 times the negative 2, that's a minus 8 plus 6. Nope, not. That would have to be 0 for those to be perpendicular. So no, they're not rectangular. They look like they're close, but they're not. They say you can do it by finding the angle between the two vectors. Much easier to just do a dot product of the two vectors. Okay? Now, all right, and we saw these are not right angles, not a rectangle. All right, so let's go back to where we left off. This is where it was, top of page 783. Okay. We finish at 110, no. 210, yeah, that's what I meant to say. 210, okay. In physics, the cross product can be used to measure torque. Okay, the moment M of a force about a point P is shown in this figure here. Okay, if the point of application of the force is Q, then the moment of F about P is, and this is a vector, it's a vector called the torque. This is the vector PQ cross with the force. Okay? Now, do you do any mechanicking at all? Not particularly. Nothing with wrenches and tools and things like that?
Yeah, I did do some of that. Thanks.
Okay. Well, I hope that you realize if you have a little short wrench and you're having trouble getting something to unloosen, get a longer handle and it makes it easier, right? That's because of torque. Because if your force is applied down here, you have to apply more force to get the twist in it. You apply it out here, then it's less force because you've increased the torque. Torque is the cross product of those two. And that's what they call a cheater bar. I don't know if you've ever seen or heard that term. If you have a wrench and it's not long enough to do what you want, get a pipe that will fit over the end of the wrench, make it a much longer. You're either going to loosen that thing or you're going to shear it off. One or the other, okay? So that's basically what torque is. The moment of F about P, the further out it is, the more torque you have. The magnitude of the moment, M, measures the tendency of the vector PQ to rotate counterclockwise, right-hand rule again, using the right-hand rule, about an axis directed along vector M. Okay, of course, if you were tightening something, you want it to do the other way. Okay, so that's what we mean by torque or the moment. And that's all they say. Okay, so they're going to skip example 4, so let's go back and we'll pick up example 4. Okay, and we'll pick it up here. Hey.
How you doing?
Good.
Speak to Dan for a moment.
What's that?
That announcement I had last time.
Yeah.
I lost it. Oh, that's it?
Yeah.
Okay, great. I was wondering what happened looking for a place to hang it up.
Oh, I
So
thought
you
you
put
said
it up
to put it up. Okay.
Yeah, I did. I
Okay.
did. Good. I didn't know you had this.
Yeah.
But this relates to that. So if you like that opportunity, by Fridays, you have to have it in.
Yeah. Unfortunately, he's the only one.
Get as many people as I can.
Yeah. He's the only one that's shown up today, or I'd have been announcing it. I forgot to say something to you, but I knew you had heard it before. So, but yeah, I've been telling the others, but Friday's the deadline, right?
Friday's the deadline.
Yeah, okay. I told my other classes yesterday.
Great.
Well, actually yesterday, the only one I had that probably would be interested was my linear algebra class, but I told them.
Yeah.
I think I may have told the trig class too, but they're younger, I think.
Students are always looking for opportunities like that.
Yeah.
In the summer.
Yeah.
This is like, what, 8 weeks, 10 weeks or something?
Yeah,
like
it's
that.
a 10-week, yeah.
You can do that standing on your head.
Right.
Make some money for the fall.
Yeah, exactly.
So I think that's the idea they have in mind anyway.
Yeah.
All
All right, Betsy. And you did get your rolls the other day. I came in looking for them, and she had picked them up. I saw she emailed you.
Yeah, I did.
Okay, good. Okay. I forgot to ask you that before. Okay. All right. So let's do example 4. Example 4 is on page, and by the way, for those listening at home, what that was all about, there's a 2019 research experience for undergraduates at UAB in experimental and computational materials research. And there's a whole group of different areas you can go in. It's a $5,000 award. They pay your room, board, and transportation once to and from UAB. Of course, that's not going to be far for us because we're so close to it. Plus, they pay $5,000 for the 10-week summer experience. You learn a lot, and the trouble is the deadline is Friday, day after tomorrow. So since you're not here today, you may not see it. Check it out. It's you can come by the classroom and see the poster. It's posted on the board over here on the side, not the one I project to, but the other one opposite the windows. It's posted there. Check it out. If you can, apply for it if you're interested. It's a great sounding program. Okay, let me move on to example 4. Page 783. A vertical force of 50 pounds is applied to the end of a 1-foot lever that is attached to an axle at point P. Okay, as shown in the figure. Okay, I'm going to have to draw the figure, I guess. Find the moment of this force about the point P when theta is equal to 60 degrees. So here's your z-axis. Here's your y-axis. Here's your x-axis. Okay? Here's your lever about the, oops, I didn't draw it tall enough. Something like that. There's the lever. This is supposed to be 60 degrees. They're showing it from the y-axis, so I'll keep it there. Okay. Now, the force is exerted on the end of this thing. There's the force, and that force is 50 pounds. Okay, doesn't matter what units you're in, but we're in U.S. customary. Okay, and it says downward, a vertical force. And they show the picture as a downward force. The end of a 1-foot lever, so this length here is 1 foot. Okay? It says find the moment of this force about the point P when theta is equal to 60 degrees. Well, in drawing the force this way, if you put it as a vector, this will be the vector 0, 0, minus 50. Right? Because it's 50 degrees down, that's in the negative z direction. I labeled these, so I forgot to label z. Okay? they put minus 50K, fine. Okay. Now, this lever that they've drawn here, they've gone 60 degrees there. Let's do the line down here. If that's 60 degrees and that's 1 foot, this is 0.5 feet. Okay? That would be in the Y direction, so that would be 0.5 J. Okay? That would make this component here, not that we're really interested in it that much. Yeah, we are kinda. This would be square root of 3 times 0.5. So square root of 3 over 2. Is that right? Yeah. Square root of 3 over 2 feet in the Z direction. Let's call that K. Okay? Now, so therefore the vector here, if the x component is 0, which it appears it is from the way they've done here, so this vector here would be a 0x 0.5 k j and root 3 over 2 in the k direction. Okay? Yeah, and that's what they got. And what they're asking for is, and this is what they're calling, before we called PK, or PQ, just so you have a sort of a reference. That's what that is. Okay? Now it's asking for, find the moment of the force about the point P. Well, their definition from before, the moment, which is a vector, is equal to the displacement cross the force. Okay? That's how they defined it. Okay? So, they're asking for the moment, find the moment of this force. It's going to be a vector. So that's going to be, the moment is going to be your determinant. Always starts with I, J, K, repeat the I and the J. Okay? Okay? And your P was the vector 0, 0.5, and root 3 over 2. Repeat the 0 and the 0.5. Okay? Then the force vector is 0, 0, negative 50. Repeat the I and J. Okay? Now, what will this vector M be? Down diagonal this way, half of negative 50 would be a minus 25 I, 0J, 0K. That was pretty easy. Then you got a 0K. So no K here, okay. 0I. Yuck. Yep, I guess that's right. It looks like mine. And 0J. So there it is. Your moment here is minus 25 foot-pounds. That's what you've been measuring here. This is going to be in foot-pounds because this was measured in feet, that was measured in pounds. Now, if you think foot-pounds, that's work, not the same. Torque is also measured in foot-pounds, but torque is a vector quantity. Work is a scalar quantity. Work is a dot product. Torque is a scalar product. Okay? And that's exactly what they got, negative 25I. They didn't put the, and they said foot-pounds. So that's going to be in the minus I direction. That's which way you're torquing this thing. By doing this, the torque is in the minus I direction. My goodness. We doubled our class size with 15 minutes to spare. Okay. Yeah. All right. We just finished doing example 4 on page 783. Sorry, we're just moving on. So the bottom of that page, they introduce the concept of the triple scalar product. What in the world do we mean by this? Okay? So here we got three vectors, u, v, and w in space. The dot product of u and v cross w, that's going to be a scalar product. In other words, a scalar number, an answer. Because this is going to cross to be a vector, and then you dot that with another vector, you're going to get a scalar. It's called the triple scalar product and is defined in this theorem right here. So here's your u, u1i plus u2j plus u3k. Your v vector is v1i plus v2j plus v3k. Very creative in their thing. W is going to be w1i plus w2j plus w3k. The triple scalar product would then be this. Remember that determinant we had before? Now this has to follow this rule. The dot product has to come first, and you put the vector being dotted with the other two. That's the top line. Then your other two, just like you did for cross product, v1, v2, v3, and w1, w2, and w3. Okay? And then you do the determinant of that. Okay? Now, I've already shown you how to do the easy way. They're going to do it with a sign change. Okay? But, hang on. Now, they say, note that the value of the determinant is multiplied by -1 when any two rows are exchanged. After two such exchanges, the value of the determinant will be unchanged, so the following triple scalar products are equivalent. Now we'll show that in just, well, in fact, they're probably going to do it on the next slide. So if you were to, say, swap these two, then you're going to wind up with the minus of what you had before. Swap these two, of course you're going to get the minus of what you had before. But swap those two, which is a double swap, and you'll get the same as before. So here's what they're going to say. Oops, no they're not, are they? Huh. So let me go on and put it here. These three would be equivalent. That one there, and if you were to, let me get this right, swap these two and then swap those two, then that would give you v dot w cross u. That would be the same value of this one. With the u cross w, that would be the opposite of it. Okay? That would also be the same as if you did w dot u cross v. Okay? Yeah. Now, rather than having to keep up with how many swaps you make, do it this way. Keep the order. Remember we did this before. U, V, W. Okay? U, V, W. U dot V cross W. That's the same as move the U down there and you have V dot W cross U. Keep the order. V, W, U. U, V, W. Just move that to the other end. Or move this to the other end and you get W dot U cross V. Keep the order U, V, W. U, V, W. Just like we did when we were doing IJK across the top. Keep the order, and you get the same thing. Cross any two of them, get them out of order, you get the negative of it. Okay. Now we go to this. If the vectors u, v, and w do not lie in the same plane, if they're in the same plane, you can't do this. Then the triple scalar product, u dot v cross w, or any one of the other two, can be used to determine the volume of the parallelepiped. That's a polyhedron, that's a multi-sided figure, all of whose faces are parallel, with U, V, and W as adjacent edges. So just like we had the cross product of V and W being the area of the parallelogram, now you dot a U with that cross product, and you get the volume of a parallelepiped. Okay, and parallel meaning that all the opposite sides are parallel, just like in a parallelogram, both of the opposite sides are parallel. Okay. Now, another way to reference this is the projection of U onto V cross W. Here's V cross W at the bottom. Projection of this onto that would then be the same. That would be this length here. Okay. And then the area of the base is this times the height. And that's what this is. So the volume of the parallelogram is the absolute value of that answer. So since you're going to do an absolute value anyway, who cares which order you do it in? Because if you get two out of order, it's going to be the negative of it. So any way that you do it, that will give you the right answer because you're going to take a absolute value of the n. So here's the theorem that allows this, the geometric property of the triple scalar product. The volume V of a parallelepiped with vectors U, V, and W as its adjacent edges is, the volume is the absolute value of the dot product of U with the cross product of V cross W. Like I just said, doesn't matter what order you do because you're taking an absolute value of it. So if you want to cross these two and dot with that, that's fine. You know, it doesn't really matter at all. Dot this with the cross product of those two. It doesn't matter which order you do or anything else, that will give you, because you're taking the absolute value, it will give you the answer. Okay? So let's see, do we have time?
I think you have like 3 minutes.
3 minutes? Oh, you're right. I'm sorry. I was thinking we ended at 20 after. We ended at 10 after. Sorry. Right? Yeah. So yeah, we are out of time. We'll start next time with example 5. Okay? Homework exercises here will be 3 or 5. They're both at calcchat.com. Either 7 or 9, they're both at CalcChat, but 7's at CalcView also. 11 or 13, they're both at CalcChat. 15 or 17, they're both at CalcChat. 15's at CalcView. 19 or 21, they're both at CalcChat. 23 is at CalcChat and CalcView. 25's at CalcChat only. And then you can start doing some of the problems. 27's the torque problem. It's at CalcChat. You can do 29. It's a little more involved. It's an optimization problem. It should be at CalcChat. And then if you want to try 31 or 33, we haven't done an example like it. You can try it, or you can wait until we finish that, and then we'll come back and do that. All right. And then 11.5, we'll move into that next time. And when we finish that, we'll go into 11.6, and then we'll be ready for the test in chapter 11. Because I don't think we do 11.7. So it may not be in 11.7. I thought there was. Yeah, there is. Cylindrical and spherical coordinates. We're not going to do those. So.
Can we do this and go to school at the same time, or is this like?
Okay. Someone asked that question of a guy who had done a program like this at A&M. He said, you're really not going to have time to do it because you do. That is very consuming. I have known a person who did an online course at the same time, but he worked his tail off, and another one who had a shorter program, like a 3 or 4 week program, and he, you know, it was in my class, so I recorded everything, so he followed what was going on while he was there, but it wore him out, but then he was able to come back. But that's a 10-week program. That's the entire summer term, pretty much, and You may start a week before we do and then finish a week early, but basically it's exactly the same time. It would have to be a night class almost, or it would have to be an online class. One of those two, and you're going to work they keep you busy all day long. It's what this other guy said. And I believe it, because he said they did field trips, they went all sorts of places and did stuff, and it required a certain amount of work after hours too. But so I think they highly discourage you taking classes at the same time. Read the material and see what they say. It may be you do it all in the workday, and so you'd have your evenings free if you want to do another class. I don't know. Okay.